Now I introduce Bellman equations. In reinforcement learning, for a given policy, an agent takes a sequence of action under the policy along an episode and receives the cumulative reward. We refer to this cumulative reward as a return along a trajectory. The goal of reinforcement learning is to find the optimal policy to receive the maximum cumulative reward or maximum return along the trajectory. According to the definition of a policy is an action based on state. So we need to learn a state by calculating its expected episodic return over policy pi. And so we define a new state value function V is the expectation of a return over the action distribution. Episode means agent from his current state, step by step, move to the terminal, and finally to win the game or successfully finish the job. Once we have this state value function, then we can substitute this return to this value function. And we split the reward into two parts. First part is the incident reward, the rest of them is the future reward. So future reward can be written as gt plus 1. So we can substitute this g into this v, we got this recursive formulation for the state value function. That means we can evaluate state value function at state s by this reward from environment and the value at the next state s prime or s t plus 1. So we follow the same idea, define another value function as called action state value function. It's defined at state s and selected action A. Then we define this value, this action state value function. And his updated equation also is by using this reward from environment and his next state and the next action. We calculate this from this Q value function update this Q function at the state for the selected action A. We call these two equations basic Bellman equations. And then we can use the Markov decision process from this backup diagram. We see what's the relation between the state value function and the action state value function. From here, we can clearly see V is here, Q is here. They are connected each other through this this policy probability. And then we calculate sum over the action A. Then we calculate from this Q function, we got this V function. And follow the same idea. See here from this Q at this point, then we have this incident reward, and then we have this state transition probability. And here is we have a state value function at a prime as a prime. So we from this V value function, we can calculate the Q. So from these two equations, we can see Q is here and they are cross each other. Then we can substitute this Q to here, and then we get another specific Bellman equation. It's called a Bellman expectation equation for the action state value function. And follow the similar way, we substitute this V into here, and we get another Bellman expectation equation. And once we have this Bellman equation, we can update, we can calculate the state value function and the action state value function at a state S. Then see how can we find the optimal policy pi. Since we have this Q value and we have this V value, then now we can find the policy pi makes this Q function maximum. And also we can find the pi, make this V function maximum. The pi makes this maximum is our optimal policy pi. So this from here we can get the optimal policy pi. So then from here, if we substitute the Q value here, V value here, we can get another specific Bellman equation. Is called optimality Bellman equation. These two equations. These two equations is just a relationship between the and the optimal policy pi, and see this is the optimal policy, and it's also we got the another pair of Bellman equations. If the environment is no, we can use a regular policy improvement method to step by step get the optimal policy. Otherwise, if the environment is dynamic, we'll have to use a special method, like an iterative method, time of difference learning, and policy gradient method to solve the dynamic environment problem. For more details, please check with this reference. Thank you. Bye.